And now just to wrap up our discussion of time complexity initially, we're going to discuss the idea of a best case and average case. So we saw in the last video that this function had a clear worst case of on, which meant that in the worst case, this grew linearly based on the input size. So as the input size grew, the amount of time required for this algorithm to complete also grew linearly proportional to that input size. Now, there's two other questions that we have. There's also a best case and an average case. We want to understand what is the best case of this and what is the average case of this. And I'll define these in the same sort of asymptotic notation as we did with this O notation here. For best case, we have this idea of omega notation. Basically, something is omega g of n if the following is true. So if for that function, it's always greater than or equal to some c times g of n for all n greater than or equal to a. This is basically just the reverse of O notation. So rather than the function bounding us above, instead what it's doing is it's bounding us below. It's acting as a lower bound. So if my function were this function here, this were f of n, then what we would have is that g of n is generally going to be as small as or lower than the function f of n. That's the idea of what this is telling us. So it's telling us the best case, it's telling us the lowest possible value that we could have rather than the highest possible value. So you see how that generally just reverses the idea of our big O notation. Then when we take a look at this function, like we did before, we could take a look at the number of operations. If you could say there's an operation here, and then inside of the loop, we really just have to do this operation once, and then we come into here and found is equal to true, and we're done, right? So generally there's like, 4 operations total that we would really have. Now, if f of n is equal to 4, it means that it doesn't really grow based on the input size at all. If we're taking a look at this equation here, we would say 4 is greater than or equal to some constant times g of n. Well, what function is closest to 4? Well, the constant function, 1, right? That'd be the closest thing, right? Calling it linear would be far too high of a growth because it would be well above 4 most of the time. So using 1 as our constant would probably make the most sense. And this equation is, of course, true for all c that are less than 4, right? So c equals 3, c equals 2, c equals 1, so on like this, right? So generally, in this case here, we could say that, well, 4 is clearly, greater than or equal to, say, 3 for all n, right? For all n that exist, really. So I could just say, for all n, right? So generally for all n, this is going to be true. So what that tells me is that this right here is going to be omega of 1, which in other words is constant time. It means that as the input size increases, in the best case, this takes a constant number of operations to complete. So the number of operations doesn't grow based on the input size, it's actually constant. So that's the idea of our best case. Now I also want to discuss our average case, which is a fair bit more complicated than either of our best case or worst case. So I'll just erase out these pieces here and we'll discuss a bit about our average case. So I'll keep this function here, this graph, because the average case really fits into it nicely. Basically, what the average case does is it says that there are actually 2 functions. So we have g1 of n, and then we have g2 of n, and g2 of n sits above our function f of n. And the idea is that rather than being above or below, the average case essentially is going to sandwich our function between it. And you can see how that could represent like an average, right? Sometimes it's bigger than a function, sometimes it's less than a function, but generally it stays between 2 areas. So it stays between 2 bounds. So that's the idea of our average case. Now finding the average case is quite tricky. And oftentimes we're not really going to go into the average case just because of how complicated it tends to be. But I'll walk you through the general idea of it when we take a look at this linear search here. So we know with our linear search that sometimes it may take 1 operation to complete. Sometimes it may take n operations to complete. And then there's a bunch in the middle here. Sometimes it may take 2 operations to complete. Sometimes it may take 3, sometimes it may take 4, and that goes all the way up until we reach n. So we have this general scale of operation range that could generally happen. And what we could do is we could take a look at the probability of each of these things happening. So if this was like a uniform distribution that all of these were uniformly likely to happen, then what we would end up with is that general sum of 1 plus 2 plus 3 plus all the way up to n possibilities, right? And really, more accurately, what we would have is the probability of these things happening, right? So really, it would be more accurate for me to say there's a 1 over n chance of this happening, a 2 over n chance of this happening, and then an n over n chance of this happening, right? And when we sum up this series, what we end up with is we end up with n plus 1 divided by 2 possibilities for the situation happening, right? So this is the general sum of this actual series here. And this would represent what happens on average. It's the expected value of this probability series. So it tells us that this is basically on average going to be n plus 1 divided by 2. If I were to simplify this, it's 1/2 n plus 1/2. And then from here, we simply apply the same sort of principles that we had. We say, well, we could drop the constants, and really this just ends up being n. We represent the average case as theta. So theta notation, so we say that this is theta n. Theta n would be the average case in this situation here. So in this case, we have all of our different time complexities. So in the worst case, this takes n operations, where n is the size of the list. In the best case, it takes one operation, or a constant amount of time, so no matter what the input size is, it always takes the same amount of time. And on average, it's also linear. So as the size of the list increases, it takes on average a linear amount of time for us to complete our algorithm here. And with that, you've now analyzed your first algorithm. You now have a bit of a better understanding of the different ways that we can analyze time complexity inside of algorithms themselves. So with that all taken care of, we're going to jump into the actual idea of discussing more about practical data structures and algorithms. We'll continue to analyze our algorithms as we go, but we're primarily going to focus more on the actual programming aspect now and see how we can solve problems with data structures and algorithms. So thanks so much for watching this video, and I'll see you in the next one.